I remembered all by myself today before I even started lecturing. It's the best I've done all week. Okay, we are going to continue with chapter 21 today. Let me pull up the slides here. I think I need to go shut Sheila's door. I could hear her interviewing somebody. She's trying to hire more people. I'll be right back. Okay, I figured if I could hear her, she could probably hear me. And I don't think she wants to hear my lecture while she's trying to interview somebody to hire. Okay. There we go. All right. So, oh, goodness. There we go. I feel like I'm situated now. We're going to keep talking about ALDOL. We have a couple more versions of the ALDOL reaction to talk about, and then we're going to move on to the next kind of family of reactions that are incredibly similar. I actually think of them as the same reaction, but instead of using aldehydes and ketones, it will be with esters. And then we'll kind of move on from there. So we talked about aldol reactions on Monday, and we did aldol addition and aldol condensation, and where we're at now are crossed aldol. So number 6, crossed aldol, and it does have 2 different aldehydes, and just like we talked about on Monday, this could be ketones. If we have 2 different ketones, it's just going to up how much or how many products there are, because it's increasing how many alpha carbons there are. So it's doubling it if there's 2 ketones. And then the other option would be 1 aldehyde and 1 ketone. So really you just need to have 2 carbonyls. When we have 2 different aldehydes, there's going to be 4 different products. And the reason for that is either one of these alpha carbons can be the one that has a hydrogen removed from it. So notice that the only other reagent is base. And we're not using one of our super strong bases. We're not using LDA or NAH. We're using one of the moderate bases because we do want to have a mixture of the enolate version and the aldehyde version or the carbonyl version. So in the 4 different reactions here, and I'm going to number the products. We have 2 columns essentially. The aldehyde that's listed in the second column is the enolate. So that is the alpha carbon whose hydrogen was removed. And then in the first column, this is the carbonyl carbon that is going to get reacted with. So another way to think about it is the first column is our electrophile and the second column is our nucleophile. And I like to kind of organize these by thinking about them, well, by labeling them. I'm going to erase my circles that are over here. I'm going to get a different color. I'm going to just number the alpha carbons and the carbonyl carbon. So 1, 2, 3, and 4. And we're going to do a practice one of these. Can't remember if I have a spot on the next slide or the one after, but we're going to do a practice one so I can show you again how I kind of organize this with the labels. But what I mean by the labels is we're reacting carbon 1 with carbon 2 in this first example. So we're taking that carbanion and we're reacting it with that carbonyl. And that carbonyl is what's turning into the alcohol. In the second example, we're reacting carbon 3 with carbon 4. So in both number 1 and number 2, number 1 and number 2, this would just be a pure aldol reaction because we're reacting an aldehyde, we're reacting an aldehyde with its same type. And then in the bottom two, we have carbon number 3 reacting with carbon number 2 to create that crossed aldol product. So the alpha carbon is reacting with that carbonyl carbon. And then in the last example, we have carbon 2 reacting with carbon 4. So I like labels, whether it's numbers or letters, whatever it might be. I have a very logical type brain, like lists make a lot of sense to me. Having that organization makes a lot of sense to me, and that's pretty common amongst scientists, amongst people that can do science and math. And so I feel like when I teach these types of mechanisms or these types of reactions, if you kind of have that checklist to go through, it can help you see what's happening, but then also when you're doing it on your own, it helps you to not miss anything or make any mistakes. It's kind of the same reason why we like decision trees, or in that SN1, SN2 chapter, it had that table at the back that kind of helped you make decisions. It's that same idea where everything's just neatly organized. Okay, let's see. I do. Okay. Couldn't remember if it was on this slide or not. So we're going to do a practice one with this. Let me find my example here. So these are the two aldehydes we're going to react together with some base, some water, and I'm going to go back up one slide just for a second. When we do see, like right here, it just lists NaOH, that's an aqueous solution. Pure NaOH is a solid, so we wouldn't ever just have pure NaOH in a reaction like this, so it's implied that it's aqueous. And then also, we're making alcohols, so if it was just a basic solution without any water in there, there are a lot of acidic hydrogens in those final structures that could be deprotonated. So with that being said, the water needs to be in there to dissolve everything, to give it a medium to react in, but then also to make sure that there's a proton source. So if the base deprotonates something, we don't want it to. All right, kind of off on a little tangent there, but an important one. I'm going to give some labels here. So I'm only labeling the alpha carbon and the carbonyl carbon of each of these. And so I can have alpha carbon number 1 bond to carbonyl carbon number 2. Actually, I'm going to scoot that up just a little. Or alpha carbon number 1 can react with carbonyl number 4. And then we have alpha carbon number 3 can react with carbonyl number 2. Or alpha carbon number 3 can react with carbonyl number 4. There's 4 possible products. That's where our 4 possible products are going to come from. Any questions so far, just on how I kind of have that organized? Okay, then let's draw some products. And I'm going to draw whatever my alpha carbon is going to be. I'm going to draw that on the top. And then my carbonyl carbon gets drawn on the bottom. And I'm going to go back a couple slides to remind you of our aldol products. I'm going to go right here. So we had two aldol reactions on Monday. We had the aldol addition, and when we're doing that reaction, we have our aldehyde, and then at the beta position, we have an alcohol. And we also had an aldol condensation reaction. And the only difference in the reagents or the conditions was that this one contains heat. So we have our aldehyde, and then between the alpha and the beta positions, there's a double bond because that heat causes a dehydration reaction or an elimination reaction, and that alcohol and the alpha hydrogen get removed. So we are looking at crossed aldol addition reactions. Keep in mind though, that if we throw a heat triangle in there, that's legit. That's okay to do. It just means it's going to go through that elimination step or that dehydration step as well. And we would get the double bond instead of that alcohol. And I'm going to give this guy a star. I forgot to do that while I was over here. We've talked about this mechanism on Monday, so it's not any different than Mondays. So let's finish this. All right, I'm going to get a different color. So I'm going to show you what now the new bonds are. So the new bond is going to go from that alpha carbon to that carbonyl carbon. Our carbonyl goes away, and we're replacing it with an alcohol because that's my alpha carbon, that's my beta carbon. Now, just like I said on Monday, that's an ugly structure. That's a really long bond between the alpha and the beta carbon, but it works. It's a correct structure, even if it's not drawn in the best way possible. It's easy to see that we had two different structures that we coupled together through that reaction. So I would totally accept that on a test. There's nothing incorrect about it, even if it's not the best looking structure. All right, we're gonna do the next one. So same alpha carbon. So I'm gonna draw that same cyclic structure. Oh, I did that backwards, didn't I? All right, let me adjust my numbers. I just realized that. No, that was still wrong. 4. I was so excited to do the crossed one. I just started with it. Sorry about that. All right. So we started with the crossed. Now we'll go back to reacting two of the same together. So same thing though, we're going to go from that alpha carbon to the carbonyl carbon. We're going to erase the carbonyl and replace it with an alcohol. And then we're going to do the same thing with the other one. So there's my aldehyde that I'm going to use the alpha hydrogen for because carbon number 3 right there. And I'm going to react it with carbonyl number 2. So again, we're going to go alpha carbon to carbonyl. I'm going to get rid of that carbonyl and replace it with an alcohol. And then last, two of the same story. We're going from alpha carbon to carbonyl. My eraser is not very precise. And replace that carbonyl with an alcohol. Questions about any of those products? Where any of them came from? My labels? My weird bonds?
Could you draw one in, the correct way? Like, how it would look if we were to, like, find it in the book or something?
Yes, so if we wanted to make it look prettier,
Yeah,
all right, I'm gonna
'cause
do the last one because it's more of a chain than the rest of them. So
okay.
if we 1, 2, 3, 4, 5. So I just started at the carbonyl, I started at the aldehyde and just numbered what looked like would be the longest chain. So I need to do a 5 carbon chain. So there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Carbon number 2 has a methyl attached. Carbon number 3 has the alcohol. And I think that's it. There's also a hydrogen on carbon number 3, but we don't need to draw that in. So this is what it would be. This is what it looked like in a more proper way. So there's our alpha and there's our beta. So that's what makes it an aldol because we have our aldehyde and then our alcohol is on that beta carbon. Does that make sense?
Yes, thank you.
You're welcome. Any other questions on these? Okay. Doing that on paper isn't horrible. It's 4 products. We can kind of mix and match and figure it out. Doing it in real life isn't the greatest though, because we don't want to have 4 different products that we have to separate. So there's a couple different ways where we can control that. We can minimize how many products we actually make. The first way that we can do this is we have only one structure with alpha hydrogens. So a common way to do this, or a common way you'll see it done, is with a benzene. So benzaldehyde has an alpha carbon. There's my alpha carbon right there. But because it's part of that benzene ring, because it has so many bonds to carbons, there's no alpha hydrogens at that location. So when we react it with another aldehyde and we add in some base, I'm going to add in my hydrogen right here, my alpha hydrogen. My base is going to grab onto that hydrogen because it's the only acidic hydrogen out of either one of those structures. We create our enolate, and then our enolate can bond to the carbonyl of the other aldehyde, the one without any alpha hydrogens. Go back over there. I drew that one a little different than the others. Was drawing in my tetrahedral intermediate. And then the last step is just to protonate that hydrogen, or excuse me, protonate that oxygen with a hydrogen. Let's try that again. There we go. Tried to draw it the same as I've been drawing them. So that's one way to control it. Another way to control it is by the order that we add them together. So do I have another blank slide? Oh, yeah, actually, this is perfect. So this is the second way. It does get a specific name. It's called a directed ALDOL addition. But this is the second way that we can control how many products we get. And we're going to do that by adding in our aldehydes one at a time. Oh, sorry, Justin. Are we good? Welcome. So we're going to not just throw everything in the beaker at the same time and mix them together. We're going to add them in a very specific order. So we're going to add in our first aldehyde, and we're going to react it with LDA. So we talked about LDA, but we haven't really seen it show up, I don't think, until right now. We're using LDA because we don't want this aldehyde to be an aldehyde anymore. We want it to completely be an enolate. So I'm going to kind of, I don't know, let's do it this way. I was going to cheat and do a half mechanism, but I'll give you a real one. So remember, LDA is lithium diisopropyl amine. So we don't care about the lithium part, but there's my nitrogen with its negative charge, and it's
So could you
2.
scroll down a bit? I can't. For some reason, my screen doesn't show the it's the compound at the bottom is cut off.
Oh, well, I can't scroll, but I can erase it and redraw it. We'll just move them up a little. Is that better? Is that cut off there? Can you see it if it's right there, Jordan?
Yes, thank you.
Okay. I wonder if it's because the little PowerPoint controls are down there in the bottom. I wonder if that's causing issues. So we're going to just steal that nitrogen, turn it into our enolate. And so this is what it's going to look like after that first step. So whichever aldehyde we want to be the enolate, that's the one that we're going to add first. So this will be the enolate. Then in step number 2, we're going to add in the other aldehyde. So by doing it this way, we've completely turned our first aldehyde into an enolate, and it's going to immediately react with our new aldehyde. And we would actually add in that second aldehyde really slowly, like drip it into the solution so that it doesn't have a chance to react with the LDA. It's only going to be reacting with that enolate. So we're going to do our nucleophilic attack. Our pi bond becomes a lone pair on that oxygen. There's our new bond. There's our negatively charged oxygen. And then our third step is water. And that water is just to add the proton back onto our oxygen there. So same mechanism, nothing new there. But this means that we are only going to get one product because that first aldehyde isn't even going to be able to react with itself because there won't be any, let me redraw some of that. There won't be any of the aldehyde remaining. It will only be in the enolate form. So we are cutting down our number of products from 4 all the way down to just the 1 by being very careful with the order that things are added in. And then if we were doing this in the lab, it would also be like how much time it's taking to add in each chemical. So this one doesn't get its own number, its own reaction number, but it does have its own name. It is a directed aldol addition. Questions about that one at all? Okay. Last one in the aldol family. Oh, sorry. Oh no, I guess this is it. I thought there would be more on the slide. Couldn't remember. The last one is intramolecular aldol. And it does say aldol condensation because notice that we have heat there. But if the heat wasn't there, we would have an intramolecular aldol addition reaction. This is still an aldol. We're still going to take a hydrogen off of that alpha carbon to make an enolate, and we're still going to react that with a carbonyl. What makes this into its own category is that the alpha carbon and the carbonyl carbon are part of the same structure. So it's just going to be a long molecule that has both of those carbons in the same structure. This is showing a 5-carbon ring forming. So we're going to talk about ring sizes and how we can get the different sizes. So I'm going to start counting right here. 1, 2, 3, 4. This is a 1,4 diketone. When we're using these numbers to describe the functional groups, we don't care about what else is on the structure. So with this structure, there's a methyl on each side, but it could be 20 more carbons on each side. We don't care. What we're saying when we say it's a 1,4 diketone is we're saying how far apart the two ketones are from each other, regardless of what else is in the structure. So I'm going to be using that labeling system as we talk about what diketones can be used for this reaction. When we use a 1,4 diketone, that can create a 5-carbon ring. And the way that it's creating a 5-carbon ring is we're going to use one of these outside alpha carbons. So you can think of the carbons 2 and 3 as the inside alpha carbons, the ones that are in between the ketones. And then the 2 methyl groups that I didn't number, those would be the outside alpha carbons, the ones that are not between the ketones, away from the ketones. So our base is going to take off that hydrogen So this is a mechanism you need to know, but it's not new. It's the same mechanism we've been doing. And our enolate is going to attack our carbonyl. Now, the way that I have this drawn, that doesn't look very plausible. They look pretty far away from each other. But remember, all of those bonds have free rotation. So even though we tend to draw them as stretched out chains, they're always fully moving. Your arms aren't always stretched out like this. You can move them around and grab your elbows or grab your hands. The molecules are the same way. They have full range of motion. So we're going to do nucleophilic attack, pi bond becomes a lone pair. And then we do a little counting here. I'm going to do this again on the next slide with some different size chains and rings. But I'm going to count 1, 2, 3, 4, 5. And I'm counting here just to see what size ring I need to draw. I know I did not stick to the same numbering pattern. They have two different purposes. Doesn't really matter. You can stick to the same one. But there's my 5-membered ring. So my new bond was the bond between 1 and 5. And then we're just adding in the rest of the pieces. So carbon 2 has a carbonyl attached to it. Carbon 5 has a methyl. And now this negatively charged oxygen. With the heat and the water that's in there, we're going to do that elimination reaction. So if I give the structure that I drew up here, or not the structure I drew, the structure that was already on the screen, the same numbering system, we would have 1, 2, 3, 4, 5. So that new bond was between 1 and 5. So this was my alpha carbon. Carbon number 5 was the carbonyl carbon. And we created that new double bond. So remember, with the condensation reactions, we're making that alpha beta unsaturation. So this is a 1,4-diketone. There's 3 others, though, that can also form rings. So I'm going to start by just putting the one we already talked about, just its name up here. That 1,4-diketone made a 5-carbon ring. The other one we're going to look at make sure I counted correctly here. 1, 2, 3, 4, 5, 6. So this is a 1,6 diketone. With the 1,4 diketone, we were using one of those outside alpha carbons. This time we're going to use the inside alpha carbon and attack our carbonyl, and we will also get a 5-carbon ring. So with this example here, I'm going to have my 5-carbon ring. Carbon number 5 still has the 6th carbon with that carbonyl attached and that methyl group. Carbon number 1 has a methyl group attached. And then between carbons 1, well, here, let's do it this way. We'll put the alcohol there. This would be the addition product. So the carbonyl turns into the alcohol after the addition. And then if we add in some heat, then we get the condensation product. But our 1,5-diketone also makes a 5-carbon ring. So we know that the other size ring, though, that's super stable, is a 6-carbon ring. So we can also make a 6-carbon ring. Again, we can do it 2 different ways because we can use either that inside alpha carbon, or that outside alpha carbon. 1, 2, 3, 4, 6. So we're starting with a 1, 7 diketone. And if we use that inside alpha carbon, we will have our 6 carbon ring. So carbon 6 is still going to have carbon 7 attached to it as a carbonyl. Carbon 1 is going to have the methyl group, and if we're doing our condensation reaction, as opposed to our addition reaction, there's going to be a new double bond. Let's see, let me erase those numbers and put them in another spot. Put them right there. We'll have a new double bond between 1 and 6 from that elimination or that dehydration step. One more. So last one. 1, 2, 3, 4, 5, 6. Oh, sorry, I only meant to go to 5 there. This is a 1,5 diketone. And this time we're going to use that outside alpha carbon. And we will again get that 6-membered ring. So let's see. Let me draw that a little bigger. So 1, 2, 3, 4, 5, 6. Carbon number 5 is a ketone. It's part of the ring, but it has that carbonyl attached to it. So I'm just moving my label in the middle there. So there's my carbonyl. Carbon number 1 has a methyl group attached to it. And with the condensation steps, the alcohol gets dehydrated and we form that alpha beta double bond. The products are going to look different because if we are using the inside alpha carbon, we will have this carbonyl that's kind of hanging off of the ring. And if we are using the outside alpha carbon, then we'll have the carbonyl that's part of the ring. Doesn't matter which one we use as long as it's an alpha carbon. So let's see. It's not that it matters which one you use, whether you're using the outside or the inside. What matters is if that you're forming a ring that's stable. So we can actually only form a 5-membered or a 6-membered ring with this. So notice our options here. We have a 1, 4, 1, 5, 1, 6, and 1, 7 diketone. So with the 1, 4 and the 1, 6, they form a 5-carbon ring. So 4, 5, 6. And with the 5 and the 1, 5 and the 1, 5 and the 1, 7 diketone, they form the 6-membered ring. So 5, 6, 7. Again, with other electronegative atoms on the chain. Possibly. So we form the 5 and the 6-membered ring because they have the best bond angles, the least amount of ring strain. Anything smaller than that is 2-strained. Anything bigger than that, it's just hard to make the right connections. They kind of miss each other if they're too big. So if we had an alpha carbon and we take off its hydrogen and then potentially there was another carbon we could react with that had like a leaving group, like we could do like an SN2 reaction. That could happen if the distance between those two were correct. So you won't see that on the test or the worksheet or anything, but that could be something with larger molecules that could be a disruption. So there's definitely a pattern here. The 1,4 and the 1,6 make 5 carbon rings, so 4, 5, 6. The 1,5 and the 1,7 make 6 carbon rings, so 5, 6, 7. The smaller number out of each one of them, the 1,4 and the 1,5, we're using the outside carbon, and the bigger number out of each one, the 1,6 and the 1,7, we're using that inside carbon. So there's a nice pattern here. This is technically not something you need to memorize though, because we can always just count. We can count our carbons. The part you would need to memorize is that you can only make 5 and 6 membered rings. You're welcome.
Professor?
Yeah.
Say I don't know, like, does this have to be done with ketones, or could it be done with like maybe an amide and then maybe like one of the like that methyl coming out of carbon 1, like maybe that's an amino group, or no?
Yes, it can be done with other stuff. And so actually where we're headed with the next reaction, the CLAISEN reactions, those are with esters. And then the last part of this chapter, we're going to look at what's called a Michael reaction. And that's when we start adding in some other functional groups. So it is definitely possible. Really the biggest difference is that when we get to this step right here, if this methyl group was a potential leaving group, then that leaving group could take off and our oxygen would reform a carbonyl. So it's very similar to the mechanisms we saw in chapter 20, where if there's a leaving group, it leaves. And if there's not a leaving group, we add a hydrogen to our oxygen. Any other questions on the intramolecular reactions? Okay. Then we are going to move on to our next one. Reaction number 8. I'm going to give it a star before I forget. Claisen condensation reactions. So in our Claisen reactions, we're going to start with an ester. So the mechanism, well, I shouldn't say mechanism, the general idea behind this reaction is the exact same as an aldol, but instead of using aldehydes and ketones, we're now going to use esters. And we are starting with reacting 2 of the same esters together, and then we're going to kind of go down the same pathway. So that we're going to use 2 different esters, and then we're going to use 2 esters that are on the same chain. So same pathway. So we're going to start with an ester. We're going to react it with some base. And the base we're going to use, whatever OR group is attached to our ester, we're going to use the same base. The reason for this is because in our product, we still have an ester. So if instead of using an ethoxide group, we used methoxide, then that means that some of our esters would get that group replaced, and some of our esters would have an OME attached to them instead, because they could go through a transesterification. It's one of our reactions from chapter 20. We don't want that to happen. We don't want to have more products. So we're just going to use the same base as the OR group on our ester. Our second reagent is just water and acid. And what we're going to end up with is called a beta keto ester. So there's our ester, alpha, beta, beta ketoester. So meaning we have an ester and on the beta carbon, there's a ketone. So let's look at the mechanism for this. We're starting the same as what we've done with all of our aldol reactions. We're taking that base and we're going to remove our alpha hydrogen. We're creating an enolate. So this is an ester enolate. It's going to do a nucleophilic attack on the carbonyl carbon of another ester. So again, right now we're just reacting two of the same esters together, but we're doing that nucleophilic attack. Our pi bond becomes a lone pair. So here's the ester portion. This, let me switch colors. Get something that stands out a little better right there. That's the new bond, that little blue line I just added in. That's the bond that is connecting my enolate ester to my carbonyl carbon ester. And that is a tetrahedral intermediate. Our ester has a leaving group attached to it. It has that OR group. So our leaving group is going to take off and our oxygen is going to reform that carbonyl. This is our product. Now, it's in a basic solution though. So this next step happens even though we don't want it to. That alpha hydrogen gets removed again by the base. And so we have that acid in there to give that hydrogen back. So we're just going to put that hydrogen back onto that alpha carbon and we get our final product. We are going to practice this one. Questions about it though before we practice it?
So the final mechanism is the one where it does a proton transfer?
Yeah.
Okay, thank you.
You're welcome. Okay, let's do a practice. And we'll draw out the full mechanism for this one as well. All right, there's my ester. We're going to react it with OET because, again, there's an F oxide attached to that ester, so that's what we want to use. Second step. Oh, forgot the number 2 there. Second step, acid and water. So I'm going to start by just drawing in my alpha hydrogen. One of the nice things about the CLAISEN reactions is that there's only one alpha carbon. So it's kind of the same thing why working with aldehydes is nicer than ketones is we only have one side to deal with. So we don't have to worry about having 2 reactive alpha carbons. We're going to grab that alpha hydrogen, make a lone pair, and we're going to make that enolate. Then I'm going to draw one more ester down here. So now we're going to do our nucleophilic attack, going from my lone pair right onto that carbon. Pi bond becomes a lone pair on the oxygen. So here's my new bond going from my alpha carbon to what was the carbonyl carbon. There's my negatively charged oxygen. So this is my tetrahedral intermediate. I don't think the book uses that term in this chapter, but that's what's happening. That is a tetrahedral carbon. It is an intermediate, so it fits. And it definitely goes along with what we talked about in previous chapters. That OR group is going to be our leaving group. ORs aren't the best leaving groups. We've talked about this before, but because we are in a basic environment still, we haven't added in that acid yet, still basic, a negatively charged oxygen is a good leaving group when we have those basic conditions. So we're going to reform that carbonyl, kick off that leaving group, and here's our final product. And this is not, again, this is not going to be the prettiest way to draw this structure, but I kept trying to keep my, let's say that again, I was trying to keep my bond angles the same so we can see those two structures coming together. And then remember, this is making a beta keto ester. So there's my alpha, there's my beta. So on that beta carbon, we have a ketone in relation to our ester. So that alpha beta bond is the new bond. As you're going through these reactions in this chapter, if you're having a hard time kind of differentiating them or keeping them separate, one way that can be helpful is as you are, looking at the ingredients, the starting material and the reagents, you can make note of what's happening, because you're going to have to be able to take this and go in reverse as well. So when we do a CLAISEN reaction, the new bond that's forming is that alpha beta bond. So making note of which bond formed, because that's kind of a big molecule that we just created, but only one of those bonds was new. The rest of them were already there. So knowing that a CLAISEN creates an alpha beta bond can be helpful in either drawing your products or taking a product and turning it back into a reactant. Looking at my notes here. Okay. Questions about that guy at all? Okay. Then let's look at crossed CLAISEN. So just like we did crossed ALDOL, reaction number 9 is crossed CLAISEN. So this just means that we're reacting two different esters together. And when we started today, we talked about the two different ways to minimize the product. So when we have a crossed aldol, we make 4 products. Is this the same CLAISEN of the CLAISEN? Yeah, it is. It's the same guy. there's so many people that get multiple things named after him, and he's one of them. But the same 2 ways that we minimize the products within an aldol, with a crossed aldol, is the same 2 ways that we can minimize products within a crossed CLAISEN. So that first way is to have only one of the compounds with alpha hydrogens. So again, we're seeing benzene being used for that purpose, because right there on that alpha carbon, there's no hydrogens. So when we react that base, that's the only alpha carbon with hydrogens. So it minimizes our products. Number 2 is to be careful with the order of how we add in our reactants. So we start with whatever ester we want to be the enolate. Reactant number 1 is LDA. So again, we're using that stronger base so that it doesn't stay in its ester form. It gets completely converted to the enolate form. Number 2 is whatever ester we want to have reacted at the carbonyl site, and then our last reagent would be acid and water so that we make sure everything is protonated. So it's essentially the same two steps, or not two steps, same two methods to have a less number of products. And then I have one more, and then we're going to do a couple practice ones here. So we can also do this intramolecularly. So number 10, intramolecular CLAISEN. This one is also called a Dieckmann cyclization reaction. So this one's named after another person. I tend to just call it an intramolecular CLAISEN. Oh, yeah, reaction 9 gets a star. It's the same mechanism. Just like reaction 10 gets a star. It's the same mechanism. So 8, look at my numbers here. Go back a couple slides. Here, we'll go back a bunch of slides. So reactions 4, 5, 6, 7 are all the exact same mechanisms. The only difference is whether or not it has that elimination step, and that would be determined by whether or not it has heat. And then reactions 8, 9, and 10 all have the same mechanism as well. So reaction number 10 is intramolecular. So again, we're going to react two esters together that just happen to be within the same molecule. Now, this one has less options than the intramolecular aldol because we only have the internal alpha carbons. So we're looking at a 1,6 diester, and it makes a 5-carbon ring because we are reacting this carbon, so alpha carbon number 2 with carbonyl carbon number 6. The other option see if I counted right. The other option is a 1,7 diester. And a 1,7 diester will give us a 6-carbon ring. So same reagents. And notice that almost all of these have had ethoxide on them. It's just very common. Whoops. Very common to use that. But if it was a propoxide or a methoxide, those are completely okay. That's just what you would have to use for your base then. So in order to use a 1,7 diester, I'm going to take my alpha carbon, going to remove its hydrogen, and I'm going to attack my carbonyl. So there's my 6-carbon ring. And I'm just going to give it some numbers and we'll fill in all the pieces. Ooh. So carbon number 1, carbon number 1 is where our carbonyl is getting attacked. So that's our reaction site. So it has our negatively charged oxygen and our ethoxide attached to it. And then carbon number 6 has the second ester attached to it. The next step in that mechanism would then be that our carbonyl is going to reform and our leaving group leaves. So here's my leaving group leaving, making it leave by erasing it. and my carbonyl takes its place. So remember with our CLAISEN, we're making a beta ketoester. There's the labeling system for that. So if we're saying it's a beta ketoester, that means the ester is kind of our home base, and then we're counting or labeling going away from that. So the alpha carbon is that linkage between the ring and that second carbonyl. And this is it for intramolecular. Because we can only use those interior alpha carbons, it limits how many options we have. Okay, we are going to practice this though. Let's draw. What are we going to practice? We're going to practice the crossed aldol. Okay, here's what we're going to react. And we are going to draw all of the products. So this is crossed aldol. We know it's crossed aldol, or excuse me, I said aldol. This is crossed CLAISEN. We know it falls into the crossed category because we're reacting two different molecules. We know it falls into the CLAISEN category because they're both esters. So this is a crossed CLAISEN reaction. How many products are we going to make?
Maybe 2.
It's going to be more than 2.
Oh, that's 4.
It is 4. So we're going to make 4. And so I have them labeled just like I did my aldol before. Alpha carbon number 2 can react with carbonyl carbon 1, or alpha carbon number 2 can react with carbonyl carbon 3, or alpha carbon number 4 can react with number 1, or alpha carbon 4 can react with 3. So I'm going to draw these very similar to what I did in our aldol section. I'm going to start with my alpha carbon, my enolate molecule on top, and I'm going to draw my carbonyl that it's reacting with underneath it. My new bond that's forming is going to bond my alpha carbon to my carbonyl. Now, because that ester has that leaving group, because it's an ester, that OR group is going to leave, and that ester is going to become a ketone. So I think I'm going to need to erase a little more than what I want here, but that's okay. Actually, let me redraw it this way. I know what I need to do. I just need to draw it in stages, not all one line. Okay, there we go. So there's my new bond. My leaving group leaves, and then I'm going to erase my carbonyl just to draw it at a better angle so it's not all jumbled together. But there we go. So that was 2 with 1. We can do the same thing as we go down the line. So here's carbon 2, here's carbon 3. So now we're doing the crossed version because they're not the same molecule. So we're going to go from our alpha carbon to our carbonyl. Because this is an ester, we can kick off that leaving group. I'm going to redraw my carbonyl at a better angle. There we go. So now we're going to use the other alpha carbon. So I'm going to go from alpha carbon number 4 to carbonyl carbon number 1. We're going to form that new bond. Leaving group leaves. We're just going to redraw that carbonyl. Last one. So we're going to start with that same structure, and now we're going to react it with one of the same type. So we have alpha carbon number 4 reacting with carbonyl number 3. So I'm going to form my new bond between the alpha carbon and the carbonyl. Leaving group takes off. And I'm going to redraw that carbonyl just to give it a better angle. There we go. So those would be the 4 possible products from this crossed CLAISEN reaction. Questions about this? Okay. Oh, I think I needed an extra screen to do that this morning. I was trying to remember why I had one more blank one in there, because that was not an original one. We're going to look at one more reaction before we're done today. Oh, no, I lied. I'm sorry. I think we're going to look at, where did we stop? Oh, there we stopped. We're going to get 2 more reactions. And we're kind of switching gears a little bit here. I feel that aldol and CLAISEN are very well related to each other. This reaction is more similar to the halogenation reactions that we started the chapter with, but we're going to do an alkylation reaction at that alpha carbon. And what we have in the center, what our starting material is a ketone. And we're ending with a ketone, but what we're going to do is we're going to add an alkyl group. And based on the conditions we use, we can add it to the more substituted side. So think of this as our Markovnikov conditions. Or we can add it to the less substituted side, so the anti-Markovnikov conditions. Let's talk about the less substituted side first. The less substituted side is referred to as the kinetic product. So that means it's the one that forms the fastest. We've talked about thermodynamics versus kinetics before. I'm going to draw you a quick energy diagram. Simple as energy diagram ever. But remember, when we talk about kinetics, we're talking about the middle of the graph. We're talking about how tall that hill is. That's what determines how fast the reaction goes. When we're talking about thermodynamics, we're talking about the start and the end of the graph We're talking about the energy of the starting material compared to the energy of the products and whether it decreases in energy or it increases in energy. And then putting those all together gives us a full energy profile. But when we put something under kinetic control, that means that it's going to be based off of speed. And so to do that, we're going to use LDA, so our very strong base, but the bulkier of the two strong bases, and very cold temperatures, negative 78 degrees Celsius. We've seen that temperature show up before, and it kind of seems like a random number that gets pulled out of nowhere. But negative 78 degrees is actually the temperature when we mix acetone with dry ice. So it's actually a pretty common temperature to use in the lab. When we react those together with our ketone, it's going to remove the alpha hydrogen from the less substituted side for two reasons. One, there's less steric hindrance. It's able to get in there and remove that hydrogen easier because there's nothing in the way. The second reason is because we're creating a carbanion, and when we have less substituents on a carbanion, it makes it more stable. Carbanion stability is the opposite from carbocation stability. We want less substituents. So this is going to remove a hydrogen from our less substituted side. Then when we react it with our alkyl halide, it's actually just going to do an SN2 mechanism. So because it's doing an SN2 mechanism, our R group can only be a methyl group or a primary carbon. So no secondary, no tertiary. And then our R group's going to go onto that less substituted side. So by using LDA, we're kind of helping that along. So it minimizes a minor product or a side product because we're using that bulkier base to encourage it to go to the less substituted side and keep it away from anything that might have steric hindrance. The other reaction is the thermodynamic product. So when we're talking about a product that's based off of thermodynamics, we're talking about energy stability. And that could be the stability of the product, but a lot of times it has to do with the stability of an intermediate. So we're going to react this with base. We're going to react it again with one of our new strong bases, sodium hydride. But notice that we're picking out the smaller of the strong bases. And we're going to react at 25 Celsius, which is room temperature. So instead of seeing 25 Celsius, you might just see RT written, which is just an abbreviation for room temperature. Our base is going to remove a hydrogen from the more substituted side. And the reason why that's happening is because we know that one of the forms of our enolate is to form that double bond, and then the oxygen gets the negative charge. I'm going to draw the other enolate over here. So it's forming an alkene as part of that intermediate. A more substituted alkene is more stable. So this is going to form the most stable intermediate it can, which means that we're going to remove a hydrogen from the more substituted side so that that alkene intermediate can be more stable. We're then going to react it again with an alkyl halide. Still has to be primary or methyl because that second portion is still an SN2 mechanism. And then our R group gets added on to that more substituted side. So we can easily control which side it goes to with temperature, and then either using a smaller base or a bulkier base. So we're going to practice this. So there's my starting ketone. We're going to do both halves of this reaction. You don't need to be able to do the mechanism for this one. Part of it's stuff we've already talked about in this chapter, and then part of it's real old SN2 stuff, so it just doesn't quite apply. Or, well, I shouldn't say that. It doesn't quite fit the pattern of other stuff in this chapter. So LDA, negative 78 degrees Celsius. And here's our alkyl halide. And then on the other side, we're going to do sodium hydride, 25 Celsius. And there's our alkyl halide. And so we want to see what each of the products are. I'm going to number my ketone. And I'm actually going to number it all the way across. The only two carbons that are reactive for this reaction, that are reactive sites for this reaction, might be a better way to put that, are carbons 1 and 3. But I'm going to number it all the way across because when I draw out my products, I want to make sure that I have every carbon. I want to make sure I haven't forgotten everybody. So it's numbered kind of for multiple purposes. All right, so with LDA and negative 78 degrees, is our alkyl group going to add to carbon 1 or carbon 3?
Carbon 1.
Thank you. So it's going to add to our less substituted side. So I'm going to just redraw my original ketone. I'm going to oh, that did not quite make a bond, did it? Let's try that again. There we go. I'm going to number those carbons the same way I did. And now this is really just for bookkeeping to make sure that we have everybody accounted for. And then we're going to do 6, 7, 8. Again, this is just to make sure that all of those carbons are in our final structure. So attached to carbon number 1, I need to add in that propyl group. So there's 6, 7, 8. So the fact that these aren't numbered in order does not matter because it's only for me. It's only to make sure that I have that 5 carbon chain from my original ketone and my extra 3 carbons from the reaction that have come together. So the bond between carbons 1 and 6, that's the new bond that formed. That first one makes sense? Questions? Okay. So if LDA and negative 78 added to carbon number 1 to that less substituted side, sodium hydride, 25 degrees Celsius, they're going to add to the more substituted side. They're going to add to carbon number 3. I'm going to put carbon number 1 over here just to give it full labels. And again, I'm going to start by just redrawing that ketone. The only thing I'm going to do a little different is that methyl that's attached to carbon number 3. I'm just going to draw it at a little bit of an angle just because I know I'm going to have to add in my new structure. So 1, 2, 3, 4, 5, and then we have 6, 7, 8, 9. So there is carbon 6, 7, 8, 9. And I know I still have that methyl that's attached to carbon number 7, but I'm going to number these first. 6, 7, 8, 9. And the reason why I'm numbering them first, so I can make sure that I'm adding the methyl to the correct one. So I'm going to put my methyl right there. So it's this methyl is the one that I'm referring to. And I just added it on right there. So we end up with a fairly bulky structure, a fairly long chain there, but we've made sure that we've counted all of our carbons and that we didn't add any extra in and we didn't forget anybody. Questions about either of those products at all? Okay. So let's see, I'm trying to decide. We only have 5 minutes, don't we? Oh, we only have 4 minutes. Okay, we'll start with this one on Monday then. We don't have quite enough time to get into it. I don't want to stop in the middle of it. So we'll start here on Monday. It looks kind of big and weird, but it's really not horrible. It's not really any different than what we've been doing. It's just getting a little bit more specific. So we'll start here on Monday. Lab today is the chapter 21 worksheet. Nothing due today. So my other recommendation is that if you haven't worked on the lab practical, the unknown, is to start that. I would highly recommend getting it done in the next couple weeks so that you don't have to worry about it when we start all of our tests. So not just in my class, but I'm assuming you have them in all your classes in those last couple weeks. I think that's it. Any questions before we close it up for the day?
Professor, I have a question.
Yeah.
For 21.3, that's the slide titled ALDOL reactions. Was the 1 and 2, were those ones starred for mechanisms? The one was like pure aldol, and then the other one was pure aldehyde.
Here?
One more up. Maybe a couple more up. Actually, I don't really know.
Well, let me tell you. So this is the first slide that's labeled aldol reactions. And yes, this one has a star.
I guess it's 4 slides down from there.
So like lower number slides?
Yes.
Okay.
Yes.
Oh, reaction number 1, you mean? Is that what you mean? This one?
I get. Oh, it's reaction number 6. 21.
Okay. Let's see what reaction number 6 is. Yes, that one is starred.
Okay.
So this one though, that crossed aldol addition,
Mm-hmm.
this is the exact same mechanism as this one. The only difference is here we're reacting 2 of the same aldehydes together, and in the crossed aldol, they're 2 different aldehydes, but the mechanism steps are exactly the same.
Okay. Thank you.
You're welcome. Any other questions for me? Okay. Then you guys have a good weekend. I will see you Monday if I don't see you in office hours.
Thank you, Professor.
Thank you.
Thank you.